Welcome to the second training video of the eGHOST project. My name is Jure Grams and I will present you the second part, the eGHOST eco-design guidelines. So we have a short introduction first, and then we will see the sustainability assessment of the case studies. We will see the eco-design action and product concepts, the sustainability results of those product concepts, and basically the main goal, the eco-design guidelines that were defined based on the results of the sustainability assessment. And at the end we have the final remark. So as it was already presented in the first part, we follow this methodology. So first we have the sustainability evaluation of the case studies for the PEM and solid oxide technologies. Then we developed the eco-design guidelines based on the sustainability hotspots. We defined product concepts where we integrated those eco-design guidelines, and at the end we also did the sustainability evaluation of those defined product concepts for the final guidelines validation. So first let's look at the life cycle sustainability assessment of the case studies. First we will look at the PEM technology, and we did the environmental life cycle assessment, and the scope of the environmental life cycle assessment was the manufacturing and end-of-life phase. Functional unit was one 48 kilowatt electric power PEM fuel cell stack without the balance of plant. Life cycle inventory was provided by our industry partner Symbio France, and the environmental footprint 3.1 was used as the life cycle impact assessment methodology. For the life cycle costing, the scope was just the manufacturing phase. We evaluated 4 production rates: 100, 1000, 10,000 and 50,000 stacks per year, and we used the same inventory as for the environmental life cycle assessment. Social life cycle assessment, we use the same manufacturing. We use again just the manufacturing phase. Inventories was the same for the environmental and for the life cycle costing. The economic data. So the inventory for the life cycle costing was referring to the production rate 10,000 stacks per year, and we use the Psilka database for our calculation. As I said, the inventories were provided by our industry partner Symbio France just for the manufacturing phase. So here you can see the table. And for the end-of-life phase, we have to define our own processes because the end-of-life phase is not that developed yet, unfortunately. So for the base case, we designed just the current state processes like open loop recycling and landfilling and so on. So we don't really have any closed loop recycling or some reuse like later on. And here we also have the inventories for the end-of-life phase. So as you can see, the platinum is the main hotspot for the environmental assessment. It's the main hotspot in 6 out of 7 indicators. Here in the legend is platinum and carbon support, but the carbon support has basically no environmental impacts compared to the platinum. What is interesting is that the mass share of the platinum is only 0.1%, and it's basically less than 0.1% of mass of the PEM fuel cell contributes the highest in most of the indicators. The production processes which include electricity used in the manufacturing phase and the water consumption are the second highest contribution to the climate change, and also marine eutrophication and terrestrial eutrophication. This would probably change if we use different source of the electricity. Here the European mix was used, but if you use like some green mix, like electricity just from the renewables, at least for the climate change, the values would be lower. So just to keep that in mind. Now let's check the life cycle costing results. the production rates highly influences the cost of the PEM fuel stack, as it's quite clearly seen on the graph. And yeah, the higher production rate reduce costs of PEM fuel stack up to 93%. The cost of materials becomes more influential with higher production rates. Yeah, because the cost of the processes itself became less significant with higher production rates, while the materials do not reduce that much. So yeah, now let's check how each material contributes to the material cost for the PEM fuel stack. And yeah, as you can see, the ionomer, gas diffusion layer, and platinum has the highest cost. Also, the shares of the cost changes with higher production rates. And yeah, the ionomer and gas diffusion layer reduces quite significantly, while the cost of platinum does reduce, but not that much. That's why at higher production rate, the platinum became the main hotspot in the lifecycle costing. Yeah. But yeah, we have to keep in mind that the costs are dependent on market, so they change a lot, especially like platinum. So it's quite difficult to assume anything. So these results should be taken with a grain of salt, because they may be correct, but they also may be completely false, but not because the methodology was wrong or anything, but just because of the situation on the market can be, you know, completely different as we assumed it at the start of the project. Here are presented the social life cycle assessment results. Again, the platinum is the main hotspot, especially for the child labor indicator. The DGL contributes the most to the only positive indicator we have, contribution to economic development. All other indicators are negative, just like for the environmental life cycle assessment. Also a quite significant contribution also have the end plates and bipolar production, especially for the fair salary and forced labor indicators. And yeah, both of them, so end plates and bipolar plates, are produced in Europe. So this is quite also like the problem for the Europe, not only just for the Asia or Africa. And if you check the absolute values at the top of the graph, you can see that the fair salary has the highest potential risk. So we will pay special attention to this indicator because this is the most critical one. So that's all for the PEM fuel cell. And now we will check the results for the oxide electrolyzer cell. Again, so this was a prospective environmental life cycle assessment. The scope was the same as for the PEM, so manufacturing and end-of-life phase. But for the case study, basically only the manufacturing phase is considered. The functional unit was one 5 kilowatt electrical power solid oxide electrolyzer cell stack without balance of plant. The inventories were based on the literature data and from the partner's expertise, and the same life cycle impact assessment methodology was used, so the environmental footprint 3.1. Here are the inventories which we gathered from the literature. And for the manufacturing phase, for the life cycle costing, only, again, same as for the PEM, only manufacturing phase was used. We used only one production rate, which was 10,000 stacks per year, and we use the same inventory as for the environmental life cycle assessment. And for the social life cycle assessment, again, manufacturing phase was only considered, same inventories, and the Silica base database was used. So the results, as you can see, the main hotspot is stainless steel. This is mainly due to the highest mass rate in the stack. Nickel oxide contributes the most to the acidification. This is basic acidification is the only indicator where stainless steel do not contribute the most, which is quite, I think. Yeah, significant impact also have the electricity used in the manufacturing process. Here, the prospective 2030 electricity mix for Spain was used, which basically includes 81% of renewable energy sources. So yeah, quite optimistic. If we go to the last cycle costing results, you can see that again the results strongly depend on the production rate. The share of cost of materials increases with higher production rate. Again, it's the same as for the PEM cell. And yeah, it basically reaches with 10,000 stacks per year. It becomes it contributes more than 50% the cost, the materials. Again, let's check which materials contributes to the to the costs. Just to keep in mind that basically the interconnects and end plates are made from stainless steel. So all this green is stainless steel, which is basically the main hotspot. What is interesting is that the shares of material stays the same more or less with higher production rate, so it doesn't really changes that much as it did with the PEM fuel cell. And we also get the reduction with higher production rate, so up to the 62%. And at the end, again, the social life cycle results. Once again, is the stainless steel the main hotspot, but here the contribution is more even than for the PEM fuel cell. Significant impacts also have the nickel-based catalyst, the lanthanum oxide, the production of solid oxide stack, and the cermet preparations. Absolute values are lower than for the PEM, but again, the fair salary is the most critical indicator. As you can see, it has basically more than 10 times higher values than any other indicator. So this was the results of the reference case, and now based on the results we defined the eco-design actions and the product concepts. So firstly, just a quick recap what the eco-design methodology is. So the methodology wants to basically reduce the negative environmental impacts without changing the quality or the functionality of the product. So to define that, we have 2 brainstorming sessions for each technology, and we defined different ideas, which were different actions, which were based on the life cycle sustainability assessment results, and also were aligned with the eco-design wheel. The defined actions were divided into short-term actions, medium-term actions, and long-term actions. We defined more than 150 actions, and we will check them out now. So first, just for the PEM, we won't go through all of them. So here are just the short-term actions. So basically, how to read this table is we have the action name, which material or component it addresses, and then here's the short description of it. And now I would suggest you to check the deliverable for further information on that, because there are just too many actions to go more in detail here. Maybe just a comment like here also the action number. The first number basically is presents the eco-design wheel axis. So we have 7 axes, and here so we have different actions for different axes of the ecodesign wheel. So we kind of address the whole wheel of these actions. So then we have also the medium to long-term actions. So we have again quite a few actions, and yeah, again, please check them out in the deliverable. So based on those actions, we define the product concepts. We define 4 product concepts: the realistic short-term concept, realistic medium to long-term concept, optimistic concept, and disruptive concept. The realistic short-term concept is based just on the short-term actions that will be realized and implemented in the fuel cell industry in the near future. The realistic medium to long-term concepts based on the short-term actions and additionally include some medium to long-term actions. Maybe just a comment here that basically every action includes every concept includes previous actions from the previous concept. So we basically just add up actions. In the optimistic concept, the concept is already under implementation by some top-end technological companies and or developed at the laboratory scale. And for the disruptive concepts, it includes relevant above-mentioned actions plus others that are still under development or in the early research or even conceptual phase. So for the realistic short-term product concept, we have the following eco-design actions. We use the recycled platinum. We reuse the stack housing. This is basically the end plates. We have the reduction in the platinum loading, and we optimize the triple phase boundary. This basically means that we have improved the efficiency of the stack. And we have the mass reductions of the gas diffusion layer, bipolar plates, and the ionomer. So yeah, then we redefine or defined a new inventory. So as you can see from the base case, we have new values for the realistic short-term concept. We have also did the same for the end-of-life phase. So again, we have to redefine it and improve it from the base case. Here we use the results from the Best for High project, which the goal of the project was to develop some novel technologies for recycling platinum and ionomer, so together for the PEM technology, and also to recover or to recycle the anode from the solid oxide technology. And since we were included in both projects, we kind of used the data and implemented it here in the eGHOST, so we get quite good results at the end. So here we used a part of the recycled platinum, and we also reused the end plates, which is shown in the red frames. And based on that, also the end of life inventory changes a bit as it's shown here. So then we have the realistic medium to long term product concepts. So the action use of recycled platinum stayed the same. Also the reuse of the stack housing, also the reduction of platinum loading. So it doesn't, regarding this, doesn't change anything, but the triple phase is optimized furthermore, which basically means the better efficiency of the stack. And we also reduce the gas diffusion layer, bipolar plates, and the ionomer furthermore. A new action is that we refurbished the bipolar plates, so we basically reuse it with a few smaller conditioning a certain percentage of bipolar plates can be reused again. So again, we have the new inventory based on those actions, and again, we have the end-of-life inventories, which are which are again improved a bit, and we have here with bipolar plates, we have some reuse of them, so not all of them goes to the open loop recycling. For the optimistic concept, the use of recycled platinum is increased. Reuse of this end plates stays the same. Reduction of platinum loading is also increased, or basically the platinum loading is reduced furthermore. The efficiency is improved again, and we also make further reduction of the gas diffusion layer, bipolar plates, and ionomer. And we can use higher percentage of reuse by bipolar plates. And we add the closed loop ionomer recycling. Again, the new table for the optimistic concept. And yeah, as I said before, the ionomer recycling, which is a new ecodesign action in this concept, was used from the Best for High project. And the last concept, disruptive concept, use of recycled platinum is increased. The reuse of stack housing stays the same. Also, the reduction of platinum loading stays the same. Also, the efficiency stays the same, but we have again further mass reduction of gas diffusion layer, bipolar plates, and ionomer, and we have a higher rate of refurbishment of bipolar plates. And we add, so the closed loop ionomer recycling is improved, and we add also the copper recycling, so the current collector is being recycled. Again, last time, the new inventories for the disruptive case, and again the end-of-life phase, we added closed-loop copper recycling, which meant that the values are a bit different in the table for the disruptive case. So this was the PEM fuel cell, and now let's go to the solid oxide. Here, let's first check the action, and again, I would ask you to look them more in detail in the deliverable. So it's basically the same concept as before. As you can see, here are a bit less actions, but nevertheless there are quite few of them. And again, we addressed all the axes of the ecodesign wheel. So here we define just two product concepts. So the enhanced realistic concept and the optimistic one. The enhanced realistic concept is based on medium-term actions that will be realized and implemented in the fuel cell and hydrogen tech industry in the near future. So this is like 3 to 10 years. And the optimistic concept includes all relevant above-mentioned medium-term actions with additional view on possible actions still under development or in the early research phase or even conceptual phase. So this is 10 years and more. So let's check the realistic concept. First, we have the reduction of stainless steel. We have use of the recycled stainless steel. We have the redesign of end plates, which is basically the mass reduction of end plates. And we have the cell shape and size optimization. And we have the mass reduction of nickel and rare earth elements. And for the end of life, we used open loop recycling for stainless steel and landfill for all other materials. So here is the inventory. As you can see, it was improved from base to realistic. And the same was done for the optimistic case. So the reduction of virgin stainless steel, or just the stainless steel, stays the same, but also the use of the recycled stainless steel stays the same, and the mass reduction of end plates is the same, but we furthermore optimize the cell shape and size, which is again basically what this means is the better efficiency of the cell, and we also further reduce the mass of nickel and rare earth elements. And the new action is the recycling of the solid oxide anode, which was, yeah, again with the Basler high. So we get the E3 stabilized zirconia and nickel oxide were basically the outputs of the recycling. Yeah, the stainless steel remained with open loop recycling and the landfill for all other materials. So here's again the inventory for the optimistic case, and yeah, that's it. So here we have now, we defined the inventories. Now the hard part was over. Now we just have to make the life cycle sustainability assessment, which will be presented, yeah, in the next slides. So we did the environmental life cycle assessment first for the PEM, then again for the solid oxide. Maybe just to revise the scope and the functional unit of the analysis. So the scope for the environmental part is the manufacturing and end-of-life phase. Functional unit for the PEM is 148 kilowatt-hour PEM fuel cell stack, and for the solid oxide 5 kilowatt electric power solid oxide stack. The inventory was provided by the industry partner in the PEM fuel cell case and from the literature for the solid oxide, and the methodology was used, the environmental footprint 3.1, and these 7 indicators were addressed. To have a better understanding of the results, maybe just check out first how the model would look like. So this is the model for the mid to long-term concept, and as you can see, we kind of defined a new life cycle phase, which is the closed loop and reuse phase. So we have the manufacturing phase, then we have closed loop recycling phase, and then we have also the end of life phase. Because if you have a closed loop recycling or reuse, that means that this could be either included in the manufacturing phase because it is an input for our manufacturing phase, or it could be included in the end of life phase because this is also basically the output of the use phase. So it could be included in both. That's why we included in neither and defined a new life cycle phase, if you can say that. So yeah, just to avoid any confusion. And then we also have the avoided impacts. Those are basically from the open loop recycling. So if you have an open loop recycling, you're putting some recycled materials on the market, which means that other industries can buy them and use them, and basically they don't have to buy virgin materials, which means that indirectly you're reducing the environmental impacts because of the reduction of virgin materials. But this is out of our scope. So we just included here the emissions which are connected with the recycling. Those are our end-of-life phase emissions. But these negative values, so these avoided impacts that are caused due to the reduction of virgin materials on the market, those are out of the scope. So we're not included into the final results, but they are basically on the graph just to show how much what is the potential reduction that could also be included some way into the analysis. So yeah, we have, as you will see, how the results are structured. so don't get too confused about that. So these are the results for the PEM fuel cell. First, we will check the relative results. The average reductions are quite high. The highest reduction is for the acidification indicator, and the lowest for the eutrophication freshwater, where basically for the short term it actually increases if you use the eco-design actions, which is a bit concerning, but this is based due to the platinum recycling process, which is on low TRL. So this is the background why we have increase in this area. For the climate change, average reductions are quite close to the reductions are quite close to the average ones, but a bit lower, especially for the realistic concept. Now we have the results for each indicator separately. As you can see, as I said before, certification has the highest reductions, and we can also check the relative shares between each life cycle stage. So between the manufacturing phase, closed loop reuse, recycling, closed loop recycling and reuse, and end of life phase. As you can see, the manufacturing phase is the highest in each product concept, and yeah, the reuse and reuse and closed loop recycling gain more, becomes more and more significant with disruptive product concept, but it's still not the main hotspot. Similar is for the climate change. The reductions are a bit lower, but basically we have like a steady reduction for each product concept. Again, here we have also the shares, as you can see, are quite similar to the acidification one. So I won't waste much time here. The only indicator that is a bit different is the freshwater eutrophication. As you can see, we have a increase here for 19% in the short term. Then in the long term, again, we have the decrease. So here we have a reduction, which is nice, which is good. And yeah, also the shares are a bit from the short term, we have really high end of life and reuse and closed loop recycling stage. They contribute quite a lot from the beginning. So in other indicators, the shares at the beginning at the realistic short term are quite low, but here they are quite high. They're still not the main hotspot, so the manufacturing phase remains the main hotspot, but you can see the obvious difference here for this indicator. For the marine eutrophication, quite similar to the climate change. So again, the percentages for the life cycle stages are also quite similar. Maybe at the disruptive case, they're a bit higher for this indicator, but not drastically. The terrestrial eutrophication, quite similar, the same case as for the acidification or climate change. So quite big reductions and quite similar shares as for the marine eutrophication. Similar for the resource use fossils, so we have like a steady reductions, and yeah, here we have a quite the reuse and closed loop recycling contributes quite a lot at the disruptive case, but still the manufacturing phase is nevertheless the most significant one. And the last indicator, minerals and metals for the resource use. yeah, here what is interesting, yeah, that basically the reuse and closed loop recycling doesn't contribute anything until the disruptive case, which indicates that basically these 11% are more or less based on the copper recycling, which is added in this disruptive product concept, which is not added before. So this was for the PEM fuel cell. Now let's check for the solid oxide. Here the average reductions are higher than for the PEM fuel cell. For the realistic concept up to 70%, and for the realistic concept up to 70%, and for the optimistic up to 84%, which is quite nice. It has the eco-design actions have similar effect on most of the impact categories, so they are quite, the reduction in all the categories are basically the same. For the climate change, it's 70%, and for the realistic, and 83% for the optimistic concept. So for those were the results for the environmental LSA. Now we go to the life cycle costing. Again, just a quick recap. First, we have the conventional LSA for the PEM fuel cell, and then a prospective one for the solid oxide technology. We included only the manufacturing phase, and the inventory is based on the environmental LCA. For the PEM fuel cell, we have 4 production rates, and for the solid oxide, just 1 production rate. We calculated the levelized cost of the stack, and we also did the eco-efficiency, which is based on the environmental LCA. So first, again, we can see same as for the reference case, that with higher production rate, the cost decreases, so up to 93%. But we are not, we are more focused on the contribution of eco-design actions, which are presented here. So we also get quite big reductions just with the implementation of eco-design action. So for the production rate 10,000 stacks per year, we get up to 52% reduction of cost for the disruptive case. And you can see those green line presents basically the threshold of 3%, which was basically defined at the start of the project, that if any product concept won't achieve that, it's not gonna be included, but we get much higher reduction than just 3% as it was defined at the beginning. So all the product concepts are quite good. And then the eco-efficiency. The results are presented for the production rate 10,000 stacks per year. So the eco-efficiency is basically the ratio between the product's value and the environmental impact caused by the product. Here we included just the carbon footprint. And as you can see, the eco-efficiency decreases, which is a good thing, meaning that each product concept is more eco-efficient. And now, for the lifecycle costing results for the solid oxide, the cost reduction is quite significant again, so 41% and 50% for the optimistic concept. The cost of bill of materials is reduced by 76%, while the manufacturing processes are reduced only by 18% for the optimistic concept. And again, all the product concept meets the threshold of 3% reduction in comparison to the reference case. We also have a quite significant externalities reductions, so up to 70% for the realistic case and up to 83% for the optimistic case. And lastly, let's check the social life cycle assessment results. Again, we only did it for the manufacturing phase. It's based on the same inventory as for the environmental and life cycle costing. We use the environmental data from the production rate of 10,000 stacks per year, and we assessed 3 tiers, so stack manufacturing, components manufacturing, and materials extraction. And we have used the Circa database, and we assessed those 6 indicators, social indicators. So, as before, the main hotspot is mining of platinum in South Africa, but as if you remember, the main problem with mining in Africa was the child labor indicator, and as you can see, we achieved significant reductions in that regard. What is interesting that basically the shift of the hotspots from platinum with product concepts, basically the hotspots shift to the plate manufacturing. So these are the end plates and bipolar plates, which are manufactured in Spain. So basically the hotspots changes from South Africa to Spain in most of the indicators. As I said before, this indicator, so contribution of the sector to economic development, is the only positive one. Unfortunately, also this one decreases. That's because we have less materials used. So basically, we pay less for those materials, which means that there is less money in those sectors that we get the materials from, or that we manufactured those components in. So the average reductions are quite high, so up to 77% for the disruptive case, which are quite significant. And here is also the absolute values to maybe get the better idea. When I said before that the fair salary is the most critical one, it still is. If you check just this light blue color, you will see that the fair salary has quite really high this bar, while the others have really low. So at the end we have more or less achieved quite substantial reductions in all the categories, except for the maybe fair salary and also the gender wage gap, which we still have quite big or quite high absolute values, unfortunately. Those were results for the PEM fuel cell, and these are for the solid oxide. As you can see, they're quite similar to the environmental one, so we achieve a really high reductions again. So 64% for the realistic one and 80% for the optimistic one. Again, the highest reductions are achieved for the child labor indicator, and that's it. So those were the results, but now we want to basically know which indicator contributes the most to the reduction of environmental impacts. So we did the prioritization of eco-design actions. So here are the results for the environmental impact. This first reduction from light green to slightly darker green is is presenting the ecodesign action 1.1 and so on. So we have 2.1, 2.3, and then all the rest actions are gathered from this last step. This is the case for the realistic mid to long term concept, and we have like quite similar impacts of ecodesign actions, except for the eutrophication, where we can see that basically one ecodesign action, which is kind of in this rest category, contributes the most to the reduction. In general, the ecodesign action 2.1, which is reduction of platinum loading, contributes the most, but we also have significant reductions from ecodesign actions 1.1, which is use of recycled platinum, and ecodesign action 2.3, which is the mass reduction of bipolar plates, gas diffusion layer, and ionomer. If the ecodesign action is affecting the same material or component, then the order of implementation of ecodesign action is important. This is the case for the ecodesign action 1.1, which is the reduction of platinum loading, and ecodesign action 2.1, which is the use of recycled platinum. So both these two actions tackle or are affecting the platinum. So it's kind of important if we first implemented the ecodesign action 1.1 and then 2.1, or the other way around. So this is an example here for the climate change indicator, and as you can see, the order does not significantly influences the contribution of ecodesign actions. There is a change, but the change is not that significant. So the ecodesign action stays, the ecodesign action 2.1 stays the main contributor, which is also presented here, where we also have the results for the economic and social aspect. For the optimistic concept, as you can see, for the climate change, the ecodesign action 2.1 contributes the most. Then also for the life cycle costing, we have the highest reductions here, and the same for the social life cycle, or here is just the fair salary indicator. So this is for the PEM fuel cell stack, and we did basically the same for the solid oxide also, where, as you can see, the ecodesign action 2.1 contributes 2.2 contributes the most, and this is the solid oxide cell shape and size optimization, which basically means the increased efficiency of the solid oxide cell. Then we also did an additional analysis, and we extended the scope and also includes the use phase into the calculation. And for the PEM fuel stack, those are the results. So here we have the optimistic product concept, and this is just the case for the carbon footprint. So we have the first bar presents the reference stack with hydrogen from steam methane reforming, and then we change the stack to the optimistic one. And first we have the manufacturing phase reduces, also the use phase or the operational phase reduces, and this is due to the extended lifetime of the optimistic product concept in comparison to the reference case. So this is this 15 in total we get this 15% reduction, and then we also change the source of the hydrogen to the green one. So we are making hydrogen from the renewable electricity, from renewable sources, and yeah, we have a quite big reduction, so 89%, but in all cases the use phase contributes the most, so more than 19% is contributed by the use phase in the case of the carbon footprint emissions. The same calculation has been done for the solid oxide. Here we also did the cost analysis, and as you can see, here the use phase is even more significant, so the importance of use phase in the solid oxide is even more critical. So yeah, those are basically the results of the life cycle sustainability assessment, and based on those results, we define the eco-design guidelines. We separated or the eco-design guidelines are structured for 6 different life cycle stages. So we have the material selection. This is one stage. Then we have the manufacturing, transport, operation, end of life, and concepts development. So first we have the generic eco-design guidelines from the eco-design wheel, and then we defined a technology-specific guidelines for PEM fuel cell, for PEM technology, and then also for the solid oxide technology. We also have like 2 time frames. So medium term, which is 3 to 10 years, which is presented in green, and medium to long term, which is more than 10 years, which is presented in purple. So yeah, here are those guidelines, again, similar to the eco-design actions. I would ask you to check them out more in detail into the deliverable. Here there are too many of them to be, so I will just quickly go through them. Maybe I will just explain. So the first is the eco-design topic, so what the eco-design action addresses. So this is like, you know, selection of cleaner materials or selection of renewable and sustainable materials and so on. Then we have the proposed actions. So those in green are for the medium term, and those in purple are for the long term. And the last column presents the actor that is basically involved. Like this, does this influences the stack manufacturer, the MEA manufacturer, maybe the European countries, or whatever. So which part of the value chain is involved here. So these are all the eco-design actions guidelines for the materials. Then we have the manufacturing, then we have the transport, operation, end of life, and for the PEM fuel cell we don't have the last one, the concept development. Similar we have for the solid oxide. So we have all these eco-design guidelines defined just for the materials, for the manufacturing, and the transport, operation, end of life, and new concept development. I would ask you again, check them out more in detail into the deliverables, where you have also like a short description of everything, and I think it should be clear enough. So just the final remarks of this presentation. So in order to define the eco-design guidelines, first we had to make a life cycle sustainability assessment of the reference case. The platinum in the case of the PEM fuel cell stack, and stainless steel in the case of solid oxide electrolyzer cell has been identified as the main hotspots. The eco-design wheel provides a generic eco-design actions, which were basically then implemented to a specific hydrogen technology. We defined 4 product concepts for PEM and 2 for the solid oxide technology. We achieved major reductions in all of the aspects in environmental, social, and economic with those ecodesign actions implemented. And yeah, then we basically defined the technology-specific guidelines in order to help the hydrogen value chain actors to better understand where the environmental, social, and economic challenges might occur and how to propose potential actions to tackle those challenges. And this is everything from my side. Thank you very much for watching. If you have any questions, please write me an email, or you can also contact me in LinkedIn. And I think this is all for the second training video of eGHOST project. I hope everything was clear, and yeah, have a nice day.